Welcome to the Advanced Fluorescence Microscopy and Image Processing course. So today is the second lecture and I will introduce you to some of the fundamental concepts of optics used in microscopy. Let us begin with the principles of image formation. So image formation in the light microscope depends exclusively on the interaction of light with matter, and matter means your sample. Okay, so when the light interacts with matter, any one of these six phenomenon can take place. Okay, so some of the light will get transmitted from the sample, some of the light will be reflected, some of the light will be refracted, some of the light will be diffracted, some light will be absorbed in terms of photons, and some light will be scattered. Okay, so most of these terminologies are quite self-explanatory, but I'll give a little more understanding on diffraction and refraction. So what is diffraction? So diffraction is the scattering of the incident light by the detailed structures of the specimen. So when light interacts with the sample, so sample have the detailed structures. So based on those details, the light will be diffracted with different angles. And another phenomenon is refraction. So refraction is nothing but the bending of the light rays because of the change in their travel speed from one medium to another. So here you can see the light ray is passing from air medium to water medium. So in the speed of light is different in the water medium compared to the air medium, and because of that, the light ray slightly bends. So this phenomenon is known as refraction, and the extent of refraction depends on the angle of the incidence light, which is known as Snell's law of refraction. So if I have to represent it by the equation, it is sine theta 2 by sine theta 1 is equals to n1 by n2, where this theta 1 and theta 2 are the angles of the incident light and the refracted light, and n1 and n2 is the refractive index of the media. So n1 is the refractive index of air, that is generally 1, and n2 is the refractive index of water. So we will see in detail what is refractive index in next slide. So now let me tell you how image position and magnification depend on lens curvature, that is a focal length, and the physical distance between the object and the lens. So let me introduce you to some of the terminologies first. So this is the biconvex lens, the blue one, and lens has a focal point. So this f1 and f2 are the two focal points of this lens. Now the distance between the focal point and the center of the lens is known as the focal length. So this small f represents the focal length, and double the distance of the focal length is denoted as 2f2 and 2f1 on this side. Now what is this A and B? So the distance from the center of the lens to the object is annotated as A, and the distance between the image and the center of the lens is annotated as B. So here is one equation which is known as Lensmaker's equation. So 1 by A plus 1 by B is equals to 1 by F, where F stands for the focal length. Okay, and if I have to calculate the magnification, then the equation for magnification is size of an image upon size of an object. So this is the image, so you have to measure the size of the image divided by the size of the object, so that will give you the magnification. So here what we are going to understand is, let's say in microscope different lenses are there, so where we should place the object or our sample to get the magnified image of the object. Okay, so you see here the object is the candle. Okay, so candle is placed between f2 and 2f2, so the lens will produce the magnified image of the object, but this is an inverted image. Okay, so here in this different diagram you can see, by changing the position of this object you can change the image size and its orientation. So let's say if you put the object between between the center of the lens and the uh, focal point, okay, then you will get the magnified image, but this is this image will form between f2 and 2f2, and image will be magnified compared to the object, uh, but it will be a virtual image. It will not be a real image. But if you put the object at exactly at the focal point, then the light will go parallel and it will not form an image. Okay. So this is the same condition like this. If you put the object between f2 and 2f2, then you can get the inverted but magnified image of the object. What will happen if you put the object at the 2f2 position, at the double the focal length? Okay, then you will get the inverted image, but the size of the image will be exactly same as the object. So there is no magnification if you put the image at 2f2 point. Okay, and here the image is further away from the objective, so even beyond 2f2, and you can see now the image is smaller than the object. Okay, so that's why in microscope also we have to align the lenses in such a way so that we can get the magnified image of the object. So let me show you one animation to help you understand this concept. So I have provided the link here, so just click on this link. So this animation or the Java tutorial is from the Molecular Expressions website. So here you can see you have flexibility to change the position of the object. Okay, so now the object is at 2f position, and you can see where the image is forming. Image is also forming at the 2f position. It is inverted and image is of the same size. Now what will happen if I move this object closer to the lens? So see, I'm moving the object closer to the lens. So see, up to this point I am getting the magnified image, the real image, but the inverted one. Okay, but then what will happen the moment this object will reach to the f point, that is the focal point? If I put the object at the focal point, this light rays will go parallel and they will not form any image. Okay, if I move it further closer, then also the rays will diverge, but they will not uh, 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 gather to make the image. So now see what will happen if I'll move the object even further closer to the lens. Okay, then these light rays are going divergent and they are not going to make an image, but on the other side of this lens, uh, these light rays can merge at somewhere here and they will produce the virtual image, not the real image. So this is, the more you move the object closer to the lens, you will see this virtual image on the same side of the object, but this is not the real image. So that's why it is very important to decide the best position of the object so that you can get the magnified but the real image of the object. So let us go back to the slides and let me show you the objective lens of a microscope from inside. So if you have seen, the objective lens of a microscope looks like this. Okay, but if you see this objective lens from inside, you can see that there are multiple lenses are present inside the objective lens. Okay, now because of this multiple lenses, it creates some kind of a aberrations. What are optical aberrations? So there can be several types of optical aberrations that take place because of the multiple lenses present in the microscope objective. So the first type of optical aberration, which is known as chromatic aberration. So here you can see the example of a chromatic aberration. So the white light is passing from this objective lens, and you know that the white light is made up of all 7 colors. So all these 7 colors will be diffracted to different extent. So all the red color light will merge at this point, whereas all the blue color light will merge at this point. So all the colors will not merge at the same point to form an ideal image. Okay, so this is known as the chromatic aberrations. Because of different colors and their different extent of diffraction, they will merge at different focal point. Okay, the second type of optical aberrations are the spherical aberrations. So this is an example of a spherical aberration. So you can see that now this is also known as the monochromatic aberration, because here multiple colors are not involved. Even with a single wavelength, like let's say if you are imaging with the green colored light or the red colored light, the spherical aberrations can take place. And why spherical aberration take place? Because of the spherical shape of the objective. So the light rays which are passing from the extreme edges of the objective lens, they will merge at this focal point 1. But the light rays which are passing from the center of the objective lens, they will merge at the focal point 3. So all the light rays, they are not focusing at the same point, but there are 3 focal points or even more depending on the from where the light rays are passing. So this creates a spherical aberrations. Then the third type of aberrations are known as chromatic aberration. So here you can see the light source is not very well aligned at the optical axis of the lens. And let's say the light source is slightly away from the optical axis, and because of that, if there is not a perfect alignment, then it may create a comet-like appearance of the point source in the image. Okay, so that is known as chromatic aberration, and because of this chromatic aberrations, you will see the comet-like shape of the point source of light. Then astigmatism. So here also the light source is not well aligned with the optical axis of the microscope system, and because of that it creates some kind of effect known as astigmatism, because all the rays, they are not merging at the same point and they are merging at slightly away from the optical axis. The another type of optical aberrations are known as field curvature aberration. So let's say the light coming from one lens falls on the other lens. Okay, now the other lens also have a curved surface. So because of the curvature of the field of various lenses, it creates this kind of image. So ideally the flat specimen surface image should be like this, but because of the concave spherical nature of the surface where the image is being projected, you will see the image like this. So this is known as the field curvature aberration. And the last type of aberrations, which are known as geometric distortion, so which can be of two types: barrel distortion or the pincushion distortion. So those kind of geometric distortions may also take place in the image. And these two aberrations, which are in blue fonts, they are known as on-axis aberration, because see, the light source is very well aligned with the optical axis. Okay, but still these aberrations can take place. Whereas the rest of the four aberrations, they are known as off-axis aberrations, because see, the light source is not properly aligned, and because of that those aberrations takes place, and that's why they are known as off-axis aberrations. So now how to get rid of these optical aberrations? So for that, various companies have designed various kind of technologies, and that's why this objective lens is not just made up of one lens which just magnifies the image from, let's say, 1x to 100x or 1x to 10x, but it also contains several other lenses to take care of these optical aberrations. So that's why, and they are named accordingly. They are named as achromat lens, fluorite lens, and apochromat lens. So let's say you want to purchase a 10x objective lens. So it is available in all three or even more versions, such as achromat objective lens or the fluorite objective lens and the apochromat objective lens. And here I have also shown the cost comparison. Like the achromat is the most cheaper compared to the apochromat, which is the costliest objective. Now why apochromat is more expensive? Because you see the achromat lens is corrected for the spherical aberration of one color and chromatic aberrations of two colors. Then the fluorite lens, it is corrected for the spherical aberration of 2 to 3 colors and chromatic aberrations of 2 to 3 colors. Whereas plain apochromat lens, is spherically corrected for 3 to 4 colors and chromatically corrected for 4 to 5 colors. Okay. Again, you can see the suffix plane in with certain objective lenses like plane achromate, plane fluoride, and plane apochromate. So this plane is added when the objective is corrected for the field curvature aberration. So see, all the plane objectives, they are corrected for the field curvature aberration. Okay, so while buying an objective lens, you should pay attention to this kind of details, that for which kind of colors and spherical aberrations they are corrected for. So if money is not a concern, you should always go for planned apochromate objectives because they are corrected for 3 to 4 colors, and the chromatic aberrations are corrected for 4 to 5 colors, and they are also corrected for the field curvature. But if the money is the constraint, then you should go for any of these achromate or fluoride or plane achromate or plane fluoride objective lenses. So let us come to this slide where we will understand certain terminologies in terms of the objective lens: angular aperture, numerical aperture, refractive index, resolving power, and resolving. So what is an angular aperture? So angular aperture is the angular size of the lens aperture as seen from the focal point. So say this is the objective lens, and angular aperture is this area which is shown by alpha. Okay, so that is the angular size of the lens aperture as seen from the focal point. So this is the focal point. So if you see the lens from this point, how the angular size of the lens will look like from this focal point. Okay, then the numerical aperture. So numerical aperture is a measure of light collected from the sample by the objective. Okay, so let's say the sample emits light in all different directions. Okay, but out of so many rays, the objective lens is collecting only this 1, 2, 3, 4, and 5 rays. Okay, so that is because of the numerical aperture. So if the numerical aperture is higher, that means the lens can collect more light. But if the numerical aperture is lower, then the lens will collect less light from the sample. So numerical aperture is a measure of light collected from the sample by the objective. And numerical aperture is a dimensionless or unitless number. So there is no unit for the numerical aperture. So generally, Na is equal to alpha by 2. Numerical aperture is equal to angular aperture by 2 when n is equal to 1. And n is the refractive index of the medium. So for air, the refractive index is 1. So Na is alpha by 2. In other words, Na is equal to n sine theta. So where theta represents the angle between the angle of the cone of the light. Okay. So higher the numerical aperture, better the light gathering capacity of an objective lens, hence better the resolution. So you should always go for the higher numerical aperture because it will provide better resolution. Because higher the numerical aperture, this objective lens can collect more light coming from the sample, and that can create a better image. Now what is a refractive index? So refractive index is a value calculated from the ratio of the speed of light in a vacuum to that in a second medium of greater density. So refractive index for air is equal to 1. The refractive index of water is 1.33 and the refractive index of oil is 1.5. Okay, so that is the ratio of the speed of light in a vacuum compared to the different media like air, water, and oil. Resolving power. It is the ability to distinguish two point sources of light placed close to each other. And resolution. So resolution is the ability of a lens to separate or distinguish between small objects that are close together. So resolution is based when the distance separating the two tiny objects is small. Okay, so here is the equation that describes resolution. So resolution, that is known as D minimum, is equals to 0.61 lambda by Na. where lambda is the wavelength of the excitation light. So see, resolution also depends on the wavelength of the excitation light. So let's say for the same lens, the resolution may be different for different color. So with the same lens, let's say for if you are imaging something in the violet color, that is, let's say Dapy-stained cell nuclei, if you are imaging, then the same objective lens can provide resolution up to 156 nanometer. But if you are imaging with a far red wavelength, that is 647 nanometer, then the resolution will be 281 nanometer for the same objective lens. So resolution of the objective lens depends on the wavelength of the excitation light. Resolving power is inversely proportional to the minimum distance between the two objects, that is d minimum, that is the resolution. So basically resolving power is the inverse of the resolution. Okay, so resolving power is equal to 1 by resolution. Lower the wavelength, lower the resolution, higher the resolving power. So make sure that you understand all this terminology properly, because we are going to use this terminology quite frequently throughout the course. So coming to the condenser of the microscope. So what is the condenser? So if you have seen this kind of a microscope, you can see a small set of lenses. They are there at this position above the light source. So this is known as the condenser. And what is the function of the condenser? So condenser actually gather the light from the light source and it focus the light onto the sample. Okay, so here you can see this is the light source and this is the condenser lens. So condenser lens actually collects the light from the light source and it focuses the light on the sample. So while calculating the numerical aperture of the system, you should consider the numerical aperture of the objective lens plus the numerical aperture of the condenser. So condenser should not be ignored while calculating the numerical aperture and resolution. So if someone asks you that what is the resolution of this microscope, so you cannot just calculate the resolution by considering the numerical aperture of the objective lens, but you should also consider the numerical aperture of the condenser, and you have to divide it by 2. So this is known as the numerical aperture of the system, which includes the numerical aperture of objective lens plus the numerical aperture of condenser. Because here you can see this is a condenser lens and the light is coming from the light source, and condenser actually focuses the light on the sample. So if you close the condenser diaphragm from B position to A position, the back aperture of the objective lens will not remain completely filled with light, and that will reduce the resolution. So always you should keep the condenser sufficiently open to fill the back focal plane of the objective lens. Okay, so let us come to the Abbe's theory of image formation. So in 1873, a German physicist, Ernst Abbe, provided some theory for image formation. So let us see what he suggested at that time. So the diffraction, when the light encounters an obstacle or opening, it creates a pattern known as the diffraction pattern. So what Abbe's big idea was, the microscope image is the interference effect of the diffraction phenomenon. Image formation depends on the interference between the non-diffracted light, the 0th order, and the diffracted light, 1st order and higher order. So let me explain what is this 0th order and 1st order and higher orders. So see, this is the diffraction phenomenon of a light. So light rays are coming parallel to the axis, and when it passes from the slit, it creates this kind of a diffraction pattern. So if you capture this image on the screen, it will look like this. So the center wave is known as the 0th order diffraction pattern. Then the first order, the first wave is known as first order, second wave is known as second order. So what Abbe suggested, the microscope image is the interference effect of the diffraction phenomenon. Okay, so I'm sure you must be quite familiar with the constructive interference and destructive interference of the waves. Okay, so the image formation in the microscope is depend on the interference of the diffracted light. The lens serves to recombine light diffracted from the specimen such that the diffracted light interferes with itself in a manner that recreates an image of the specimen. So that is what Abbe suggested, that the objective lens actually uh, serves to recombine the light diffracted from the specimen. So specimen will diffract the light like this, and the objective lens will try to collect the zeroth order light, first order, second order, third order. More the diffracted light it collects, the better the image it can produce. So here you can understand that thing in little better way. So let's say this is the specimen plane. Here the sample is there, and this is a cone of light from the illumination source. Okay, now you can see the orange rays are these represents the zeroth order uh, light, whereas the red rays represents the higher order of diffraction. Okay, and this objective lens is collecting zeroth order light, first order, second order, and third order light for the image formation. So getting the highest resolution image depends on capturing the largest angle of scattered light. Okay, so you must have heard that for some of the microscopy applications, we use oil immersion objective lens. So why oil immersion objective lenses are used? So you can understand that thing in this diagram. So see, this is the light source. Here is your sample, and here is your 100x objective lens. Now this is the oil immersion objective lens. So that means a drop of oil was kept between the slide and the objective lens, and this is the air objective lens. So that means there is air between the slide and your objective lens. So because of the presence of air, what will happen when the light rays coming from your light source, okay, when they will pass through the sample, they will diffract it more because they are entering from one media, that is a glass, from the other media, that is air, and then they will enter into the objective lens. So only a few rays can enter into the objective, and most of the rays will get diffracted. Okay, but if you put a drop of oil between the glass slide or your sample and the objective lens, then the refractive index of this immersion oil is equal to the refractive index of the glass slide. So because of the same refractive index, rays will not bend or they will not change the angle, and they will pass all the way through the objective lens. So that way the objective lens collect more diffractive light compared to the air media. Okay, and that's why oil immersion objective lenses gives better resolution. They have a higher numerical aperture because they can collect more light from the sample compared to the air or water immersion objective lenses. Similarly, another scientist, Raleigh, also provided some criteria for resolution. So the Raleigh criterion specifies the minimum separation between two light sources that may be resolved into distinct objects. So when two point sources are very close to each other, their airy disks will overlap and they can't be easily resolved. So let me explain what is airy disks. So this is the diffraction pattern of a light point source of a light. Okay, so that, let's say these are 2 point sources of light which are placed very close to each other, and this is the diffraction pattern. So this is the zeroth order light and this is the first order light. Okay, so this is known as airy disk. The center is known as the airy disk and the ring is known as airy ring. So how Raleigh defined this criteria for resolution? So it is only possible to resolve a pair of sources if the central peak of the two diffraction patterns are no closer than the radius of the airy disks. So what he is saying, like, you can resolve only 2 point sources when the central peak of both this diffraction pattern are no closer than the radius of the airy disk. So see, this is the radius of the airy disk. Okay, so if the center peaks are that much apart, then you can resolve these two sources as 2 point sources. But if the central peaks are are not separated by this distance of radius, okay, then you will consider this, you will not resolve this object. It will appear like a single dot. Okay, so Rayleigh equation for calculating the resolution is 1.22 lambda by 2n, where lambda is the wavelength of illumination and n is the numerical aperture of the system, that is numerical aperture of objective plus numerical aperture of condenser divided by 2. So again, let us understand some more terminologies: Airy patterns, limit of resolution, and point spread function. The limit of resolution of a microscope objective refers to its ability to distinguish between two closely spaced airy disks in the diffraction pattern. Three-dimensional representation of the diffraction pattern near the intermediate image plane are known as the point spread function. So see, if you put any point light source in the microscope, you will get the image like this. You will get the diffraction pattern of that point light source. Okay, and that's why you can see this kind of airy disk and airy rings, because these are the diffraction pattern of individual point source of light. Okay, now you can see that these are the resolved airy disks, but if this airy disks are merging like this, then this is the unresolved structure. Okay, and the 3D representation of this is known as the point spread function. So this is the point spread function is nothing but the 3D representation of this airy disk and airy rings. Okay, so till now we saw three equations for calculating the resolution of a microscope, which is known as d minimum. So d minimum can be calculated by this equation, lambda by 2na. It can be calculated by 0.61 lambda by 2na, and also 1.22 lambda by 2na, that is na of objective plus na of condenser. So for the same wavelength, let's say 488 nanometer and the numerical aperture of 1.4, if you calculate the resolution, all three equations will give you slightly different numbers. So equation 1 will give you 174 nanometer, equation 2 will give you 213 nanometer, and equation 3 will give you 212 nanometer. So while comparing the resolution across different microscopic systems, you should make sure that the resolution is calculated using the same equation. It should not be that for one microscope you calculated using this equation and you are comparing it with the other microscope for which it was calculated using the first equation. And you can see there is no significant difference between the equation 2 and equation 3, but if you have calculated using equation 1, then it's a significant difference. So this value is known as the diffraction limited resolution of a microscope. What does it mean, that diffraction limited resolution of a microscope? That means if I put any object smaller than this distance, like 212 nanometer or 213 nanometer, any object smaller than that will give me the image of 212 nanometer. So let's say my point source of light is just 10 nanometer in size. Okay, but the image that I will get, it will be 212 nanometer. Okay, it will not be actually 10 nanometer. Okay, because I am going to see the diffraction pattern of that object, not the real image. Okay, so to explain this, I will show you this slide. So this is known as the diffraction limited resolution of a microscope. So see, here the specimen are of different sizes from 18 nanometer to 138 nanometer. Okay, and below the microscope images are shown for this different size of the specimen. Can you see any linearity in the size in the image? No. The 18 nanometer object can also produce the image like this. Okay, whereas the 138 nanometer object can also produce the image like this, because the diffraction limited resolution of a microscope is 212 nanometer. So any object smaller than 212 nanometer will give the image like this. If let's say there are two objects of 50 nanometer lying close to each other, I will see the image like this. Until and unless they are separated more than 212 nanometer, I cannot see them as a two different objects. I will see only one, this kind of a diffraction pattern. Okay, let's say here four objects of 10 nanometer are lying close to each other. Okay, but in the microscope image, I will see only a single diffraction pattern because they are within 212 nanometers. Okay, so this is known as the diffraction limited resolution of microscope. So whatever you do, but you cannot go and resolve the structures beyond 212 nanometers. So little more understanding on the point spread function. So what is a point spread function? So let's say this is your real object, okay, the point source of light. So ideally you expect the image to be like this, okay, but actually in the microscope you will get the image like this. You are seeing the diffraction pattern of this real object. You are not seeing the real object, you are seeing the diffraction pattern of this real object. This is the 0th order wave, this is the first order diffraction light, and maybe the second order diffraction light. And if you see this in the orthogonal view, again it will not show you the point like source, but in the orthogonal view it will give you this kind of an image. So this is known as the point spread function of the point source of light. So now let me explain you about Kohler illumination. So Kohler illumination is a method of aligning the optics in a microscope that provides even illumination across the field of view. It maximizes contrast and minimizes artifact. So here you can see, let's say if you are sitting on a new microscope and you are trying to focus your cells for the first time, and if you are seeing something like this, that only in the entire field of view only a small part is little bright compared to the periphery. Or you can see here, let's say this is the image, but only a small part is shows the bright image compared to the rest of the area. So this is known as the microscope is not properly aligned. Microscope objectives or the light sources are not properly aligned. So Kohler provided the method for aligning the microscope for proper illumination of the entire field. So this is known as a Kohler illumination, that your field should be should provide the even illumination at every corner of the field. Okay, so let us understand the critical parts and pieces of the microscope. So let's say this is the light source, then this is the collector lens, then this is the condenser lens, and then this is your sample. Okay, so here the sample is red. Okay, and this is the objective lens. These are some tube lenses followed by eyepiece, and here is your eye. Okay, so now see, on your eye you want to project the magnified image of the object. You do not want to project the image of this light bulb, okay, or the filament of the light bulb, because see, if you align the microscope lenses in such a way, then you will start seeing the image of this light bulb or the filament of the light bulb on your eye, okay, instead of the sample. But you have to align it in such a way so that you can see the image of the object and not the light source. Okay, that is known as the Kohler illumination. So let us understand the conjugate image planes. So at what plane the image of the light source is found? So let's say this is a light source, then it passes from this lens, and again the light rays are merging here. So here you can see the filament of the bulb. Okay, again you move further, and here you are seeing the merging of the light rays. So here you can see the filament of the bulb. Again this light rays are merging closer to your eyes. So again here you can see the filament of the light bulb. But you can see that here your sample is evenly illuminated. Now if you move the position of these lenses up or down, or maybe left or right here, then the bulb filament will be focused at the sample. Okay, so we do not want that. We don't even illumination of the sample. So you should focus these lenses in such a way so that sample is evenly illuminated like this. Now see, these are the conjugate image illumination planes. Now let us see the conjugate image plane, on which plane the images are formed. So see, this is the sample. Then those sample rays are aligned again merging at this position. So this is known as intermediate image plane, and then further they are merging on the retina of your eye. So here the image formation takes place. Okay, so you will see the magnified image of the object and not the filament of the bulb. So if you merge both these planes, conjugate image planes and conjugate illumination planes, then the diagram looks like this. So you see how the microscope optics are aligned. so that at alternative positions, either you can see the image of the bulb filament or you can see the image of the object. So the overall idea of this Kohler illumination is that you should align your microscope lenses in such a way so that your sample should be evenly illuminated, and in the image plane you should not see the image of the bulb filament. Instead, you should see the image of your object. So that is the purpose of Kohler illumination. So whenever you sit with any microscope for the first time, the first step you should do is align your microscope optics for the Kohler illumination. And see, this Kohler illumination is only important for the transmitted light microscopy and for the bright field illumination. It doesn't work for the fluorescence imaging. Okay, so this is just to see the cells in the bright field. It will not help you, even your microscope is not aligned for the Kohler illumination, it will not affect your fluorescence imaging applications. Okay, so let us end this lecture with this. So our next class, we will discuss about designing of a fluorescence microscope. Okay, so see you soon. Thank you.